Ladies and gentlemen, the e-seminar is starting. Aaron, please go ahead.
Hello and good day, everyone. This is Aaron Goldberg, and I'm going to be your moderator today, where we're going to take a look at a crash course in MPP databases for analytics. Now, analytics has become a critical activity in most organizations. We see not only an increasing value and use of the expert data scientists to provide game-breaking analytics for an organization to perform better and more successfully, but we're also seeing the rise of citizen data scientists as well. In general, the use of analytics is, frankly, exploding. So we're going to learn more about how you can get more value and how you can do some new things with analytics that maybe you hadn't thought of before or hadn't had the technology to work with. I'd like to thank our sponsor today, Looker, because without them we don't get a chance to provide you with this great information. And in addition, we have two expert speakers with us today. Jake Yost and Daniel Mintz are both from Looker, and I'll be turning over to them in just 1 minute. But before I do that, what I'd like to do is help you get a little more value from today's presentation. There are three things that you can take advantage of that I think will help you get more from the time you're going to spend with us. First, you can ask us your question, make an observation, even a comment. You'll see your Ask a Question box on the console. All you have to do is type in your question, comment, or observation, hit submit, and we will see it. And we'll get to your questions during the live Q&A at the end of the event. Now, the good news here is if we don't have time to get to your question live, what we're going to do is get back to you with a written email response. So don't fret. If you don't hear your question, you will get information back. So do take advantage of that feature. Second, you can download a PDF copy of today's presentation. I think this is a best practice. Why? Three key reasons. First, it's something you can share with your peers in your organization so they get value from today's event. Second, you can take notes on it and you make it even more focused on your needs and issues. And third, it's a persistent reminder of today's event, something easy to find so that you can review information you've learned with us today. And finally, you can also use your social networking tools. You can tweet and share. You'll see support for those on your console as well. And one last thing is that if you click on your resources button, you'll see some more informational resources that are there that you can download and take advantage of as well. So with that, let me get out of the way, and I'm going to turn it over to Daniel, and we can get started. So Daniel, over to you.
Thanks so much, Aaron. So as Aaron said, today we're going to do a sort of crash course in MPP databases for analytics. I'm Daniel Mintz. I'm the Chief Data Evangelist at Looker and was actually a customer of Looker's for 3 years and have used a number of these databases in real life, so I'm speaking from experience. So, just to sort of go over the agenda of what we're going to talk through today, what you can expect to get out of this. So first, I'm going to start by giving a sort of background basics of MPP. I'll probably start with, what does MPP stand for, and we'll go up from there. I'm going to talk about columnar data and what that means and why it matters, why MPP databases organize their data that way. And then we're going to sort of dive into classes of MPP databases, and we're actually going to talk through 4 specific MPP databases that we see a lot of folks using today. Jake's going to talk about Redshift and Vertica, and I'm going to talk about Snowflake and BigQuery. There are a lot of other MPP databases out there as well, but those are the 4 I would say that we see most folks using. And we'll talk about some of their strengths and weaknesses and sort of where they came from. Then we'll talk about some best practices for analytics and how they relate to MPP databases, give a little bit of a wrap up and our 2 cents about sort of where we see this going and sort of how people can best take advantage of this technology. And then we'll leave plenty of time for questions and answers. And as Aaron said, if we don't get to your question today, we'll make sure to get back to you with a written response. So let's start with some basics. The first thing I should probably say is what MPP stands for. So MPP stands for Massively Parallel Processing. So a massively parallel processing database is one that has lots of processors, as you might guess from its name, and where all of those processors work in parallel. So what that means is that the workload that you are asking the analytic database to complete is broken down into smaller chunks and handed out to however many nodes you have in your MPP database cluster. And so basically you're taking one big job, splitting it up into a bunch of smaller jobs, and then collecting and collating those results before you pass them back to the user. You know, historically, MPP databases have been shared nothing architecture, which is to say that you know, each node in the cluster, each individual member of the cluster has its own memory, its own processor, its own data store, you know, its own storage. There have been some advances in architecture that we're going to talk through, and some different approaches, each of which have some strengths and some weaknesses. So we'll talk through that. And it's important to notice, or to note as well, that, you know, MPP, this basic idea of massively parallel processing, is not just a data concept. It's actually something that's used a lot for supercomputers as well. You know, there are a number of supercomputers that are technically MPP supercomputers. So this basic idea of taking a larger workload and splitting it into a bunch of smaller workloads is one that has a lot of currency across the computing space. So before we look at sort of how an MPP database is architected at a basic level, I want to talk about what a standard non-MPP RDBMS is. So RDBMS stands for Relational Database Management System. And, you know, RDBMSs are normal sort of SQL-based databases. So everything from PostgreSQL to MySQL to SQL Server, you know, and many flavors in between are non-MPP databases. They are standard RDBMS databases. And the way that they generally work is that you have a SQL client of some kind. You write SQL in it. That SQL gets passed to a query language processor, which turns it into interpreted SQL, passes it to the engine, which comes up with an execution plan, checks in with the file and transaction manager, and makes sure that there are no other transactions interfering that it has to wait on. Once it gets the okay, it sends that execution plan to the physical database, which executes it, comes up with the results to the query, passes it back through the chain and back to the SQL client. So it's a pretty straightforward, pretty linear system. As compared to an MPP database, and obviously every MPP database has somewhat different architectures, but this is just a sort of useful sample. So as you can see here, we start with the SQL client, same basic idea. And, you know, so we pass SQL in, we write SQL into our SQL client, and that SQL gets sent to a master node. And there's generally only one master node. And that master node is sort of the coordinator. It's responsible for doing a bunch of important stuff. So it manages transactions, and it also sort of keeps the data dictionary. It keeps track of what's going on in all of the shards or nodes that live underneath it. And it also comes up with the execution plan. So, you know, coming up with the execution plan is not generally the hard part of processing a query. Generally, the hard part is actually executing the plan. And so the master node is the one that comes up with the execution plan, and then it passes that execution plan off to all of the different shards. And, you know, there can be, you know, 1 shard, 2 shards, 5 shards, 10 shards, but there could also be hundreds of shards or even thousands of shards or nodes. And so each of those executes the plan and then passes back their individual results to the master node. The master node takes those results, collects them, collates them, does whatever it needs to get the actual results, one single result to the SQL query, and passes that back to the client. So the split generally happens sort of after you've passed that master node, and that's where you can take advantage of this MPP architecture. So in terms of a history, you know, the sort of first MPP databases that we saw are actually all the way back in the 1980s. Teradata is usually seen as the first true MPP database. Later in the 90s, we had things like Netezza, and, you know, these MPP databases gained some following. You know, they did things on the analytics side that had been, you know, very difficult or impossible, but they were somewhat limited. They certainly didn't gain the same traction that more recent MPP databases have gained. And, you know, what you see is because data volumes were growing, you know, through the 90s and into the early 2000s, people started looking for a system that could process huge volumes of data, and what they ended up with was often Hadoop-based. And so you see the rise of sort of Hadoop systems in the 90s and, well, in the early 2000s. And, then you see with the advent of PostgreSQL, which confusingly also has an elephant, just like Hadoop, but with PostgreSQL, which is an open source implementation of SQL, that sort of kicks off a second wave of MPP databases. And so because PostgreSQL is open source, the second wave of MPP databases starts to come into existence in the sort of early 2000s, and they are often built on top of Postgres. They use Postgres as their language. And so you see databases like Parcel and Greenplum, and unlike the sort of first wave of Teradata and Netezza, these really start to get a little bit more currency. And they start to take off, and they start to challenge the Hadoop ecosystem in their ability to handle huge quantities of data. So we've come a long way since Parcel and Greenplum, even though they're the second wave. And so what we're talking about here is kind of the third wave. But that's sort of how we got to where we are. So thing I want to talk about is sort of why MPP, why do we like it, what is it good at? And the first thing that MPP databases are good at is performance. They are fast, and more than anything else, that is their sort of defining characteristic. They can handle huge quantities of data. They can easily handle billion row tables or 10 billion row tables or even 100 billion row tables in a way that a transactional RDBMS never could. And so for analytic workloads particularly, they're really a new sort of way to handle this much data. The second thing that they're really good at is they're really good at structured data. This is true of RDBMSs as well, but it's important to note that MPP databases really are great when your data is in a tabular format, when it's got rows and columns. The third thing that they're good at is in general, they tend to be pretty low maintenance. MPP databases, because you've got all of these worker nodes, it generally is not a huge deal to replace one of those worker nodes if it falls down. And so the maintenance costs of keeping them up and running are not huge. And then the last and probably most important thing that MPP databases bring that they're good at is they speak SQL. And SQL has been around for 40 years now, and it is really the lingua franca of analysts. It's something that most analysts are familiar with in one form or another. And so, I think one of the places that Hadoop has had trouble gaining ground in the analyst community is that, in general, Hadoop doesn't speak SQL. Hadoop speaks some version of Java. And so your ability to sort of write code and iterate on it is limited, and you need a different skill set than the one that analysts often come in with, which is SQL. So those are the things that MPP databases excel at, the things that they're not so great at. So one thing, as you might have guessed when I said that they're good at structured data, a thing that they're not so good at is unstructured data. And this is one place where Hadoop really, excels and the MPP databases don't. So MPP databases just aren't great with unstructured data, things like text or video or images. That's something that Hadoop often has tools for managing very well. And we'll talk a little bit about sort of some advances that we've seen, at least on the semi-structured data side. But, in general, historically, MPP databases have not done a great job with unstructured data. The second thing that they have historically not been great at, though this is changing, is scaling. Whereas a Hadoop cluster, you can sort of scale up a Hadoop cluster from nothing pretty quickly and scale, a very large one for one workload and then a very small one for another. MPP databases, it has generally been somewhat onerous to scale up or down. And the reason is just because each node sort of shared nothing, you had to redistribute the data across however many shards you had. So if you had 5 nodes, 5 shards, and your data was, 20-ish% on each of them, if you scale that up double to 10 nodes, all of a sudden now you need 10% of your data on each of them, and that involves moving a lot of data around, and so that takes time. And then the third thing that they have historically not been great at is just changing data, things like running updates or deletes. And this is a function of the way that MPP databases store and organize data. And so I'm going to dive into that because I think that's really critical. So, the key thing to know about MPP databases is that they tend to organize their data in a columnar store, so by column. So this is a row-based data set about the presidents of the U.S. And so, in a row-based data store, that means that when you go down to the memory level, each row is stored together. So George is stored next to Washington, is stored next to 1789, is stored next to 1793, is stored next to Virginia, is stored next to Mail. And that's great for certain applications, but it's actually not that great for analytics. And so what MPP analytic databases have done is they've sort of turned that 90 degrees, and they store their data instead as columns. And so what that means is, for home state, for example, instead of storing that along with the name of the president and what year he entered office and what year he left office and all of that, home states are all stored together for all rows. So, you get in memory, VA, VA, MA, VA, and so on and so forth. And that has some really key implications, which I'm going to walk through because they really are important for understanding how you can best utilize MPP databases. So the first sort of most basic one is that if you're in a row-based context in a sort of normal RDBMS, selecting all of the columns from a particular row is a pretty fast query in general because, of course, all of the columns from that row live together in memory. So you find them where they live in memory, grab them, and present them. On the other hand, selecting a count of all the rows can be slow. There are lots of databases like MySQL that have sort of workarounds that make it fast, but in general, traversing all of the rows of a table means actually traversing all of the data because you have to scan through each of those rows. Now, if you're working in a columnar situation, it's actually exactly the opposite. So if you want to select all of the columns from one row, that's often quite slow on a columnar data store on an MPP database. And the reason is because each of those columns is stored in a different place. So if a table has 40 columns, then it needs to, just to find all of the columns for one row, it needs to go to each of those 40 places and grab one piece of data. Now, select count of all, on the other hand, is really fast. And that's because it only needs to traverse one column of the data, and it can do that very, very quickly because if there are 1 billion rows of column A, we know that there are going to be 1 billion rows of column B and column C and column D. So that's one important thing to keep in mind. A second thing to keep in mind is that certain patterns that you may have learned are bad in row-based stores are totally fine in columnar stores. So for example, a sort of sparse matrix of data where you have lots of null values is something that's not a great practice with row-based stores because you will end up fetching a lot of columns for a row that are not don't have any data for them. So, if you go fetch any of the rows in this imaginary table here, you will inevitably be fetching a null, and that's not great because that's kind of a waste. Now, if on the other hand you're fetching something from the columnar data store, you might say, I want to see all the values for attribute 2 where type equals A. And so you're going to fetch row 1, row 3, and row 4. And so attribute 2 for those all have values. You're not getting any nulls. And you're not going to look at attribute 1 at all because you're using a columnar store. And so it says, well, they didn't ask me anything about attribute 1, so I'm not going to bother to go get that data at all. So that's something that you need to keep in mind when you're sort of thinking about how to design tables for MPP databases, is that some things that you may have learned were bad practice are actually totally fine for columnar stores. Another thing that it tells us is storing data in columns makes sorting it really important and sorting it properly really important. So let's say that you were scanning this table of presidents and you wanted to see all the presidents starting with a start year after 1900. That's really easy for the database to do because it has indexes on each of these columns, and it can find the row that contains start year where start year is greater than 1900. It can go directly to that and then kick off from there. So the way that the data is organized tends to be really important. Another thing that it makes really important is compression. Because data is organized in columns, it means that the data in each column, the data stored together in memory tends to be of similar types, right? So, if you look at the first column, you might create sort of a dictionary of keys here and say, well, first name George is key 1. And so instead of writing George, we're just going to write key 1. So that's, the first 2 rows each have key 1. The third row has key 2. The fourth row has key 3. And by the time you get to Barack in the last row, the 44th row, you've actually only encountered 27 distinct keys because there have only been 27 different first names for presidents. Another example, if you look at the start year or the end year column, and this is something we see a lot, rather than storing the full year, sometimes we store the delta, the difference between each row and the row above it. And so that takes up a lot less room in memory. It's much more compressed. And what that means is that you can store more data in a particular place in storage, which means when you go to access it, you can access it much more quickly. So compression tends to play a really big role in the way that MPP databases optimize their data access. And then the last two things I'll mention before I hand it over to Jake is, that when you're writing queries for MPP databases, one of the other things that you need to keep in mind is each extra column that you want to access has a cost. And so, for folks who've written lots of queries for row-based databases, you probably know that however many columns you include in your select probably doesn't have a huge impact on the performance of the query, how quickly it returns, right? What tends to matter is, well, how many rows are being addressed? Now, that's not true for columnar. If you start addressing more columns by including more of them in your select, that's going to tend to make your query return slower because, if you look at select column 1 from a table versus select column 1, 2, 3, 4, 5 from a table, it's actually having to go get 5 times as much data. And if you didn't include those columns in your select, it wouldn't bother getting them at all. It wouldn't look at them at all, and so it would return much faster. So these are just some of the sort of key things to keep in mind when you're thinking about columnar. It really is a different way of thinking about data that's much more suited to transactional workloads. So now I'm going to hand it off to Jake, who's one of our sales engineers who works on the alliances team. So works with a lot of these technology vendors, and he's going to walk us through some of the sort of classes of MPP databases and some of the ones that we see most often.
Great. Thanks, Daniel. So we've decided to break MPPs roughly for the purpose of this talk into 2 classes. And to begin with, I'm going to start to talk about managed MPPs. And then I'm going to hand it back to Daniel to talk what we're going to call about on-demand MPPs. And then I'm going to first kind of define what managed MPPs are for you, and then I will dive into 2 specific instances of MPPs, Redshift and Vertica, and kind of talk about the differences and the way we think about them. So to start with, when we talk about managed MPPs, we're really talking about databases where you're going to provision a cluster to store and compute your data. And that can be in the cloud or it can be on premises. The important thing when you're looking at these managed MPPs is to think about the data that you're going to put in there and understand how much you're going to use and what your growth plan is, because you're going to be managing this. With managed MPPs, you have some levers that you can pull, and that's a lot of what I'm going to talk about next is how you can optimize these to run. Because MPP databases operate slightly differently, like Daniel just went through, we need to think about how we store the data, how we sort it, and that type of thing. So I'm going to talk about that in a second, how we optimize those. And then here's some examples of managed MPPs out there. So Microsoft Azure, Greenplum, and then like I said, I'll talk about Vertica and Redshift. So regardless of the type of managed MPP, you're going to run into a few things that you're going to want to think about and organize as you load data and access it. And the first thing that you want to think about is distribution. And so on the left-hand side, we've kind of put all of our data, our little gophers, in one place. And that can be nice in the sense that communicating between nodes is expensive in a database because you're writing across a network. And so if I have all my data in one node, it's really fast because I'm not communicating across that network. On the other hand, that doesn't buy us any of the advantages of an MPP. We might as well just have a standard database if we're just using one node. So we want to spread the data across different nodes so we can leverage that parallel architecture. But we see on the right-hand side there, now my gophers have to kind of cross over across nodes and talk to each other, and that's going to take time. And so when we think about distribution, we want to be able to make a blend of data existing across the network, but also keeping the data that needs to be processed together on the same node so that you can speed up your query time and so that joins and order by and all those things can happen very quickly. So if we think about distribution as how to store data across different nodes, the next thing we want to think about is how to store data within a node. So this is going to be what we call sort. And this leverages that idea of columnar concepts that Daniel was talking about. Because the data is stored in columns, we can skip large chunks of data to get to what we need. And so storing the data based on what queries you're going to be writing is very important. What we commonly see, and I'll talk about this more a little later, is that we want to use a time or a date as storing because it's a very common way to access data by this quarter or last quarter. And that'll allow us to just get to the data we want. And then also something that Daniel mentioned that we want to think about, a lever that we can pull as we're trying to optimize these databases, is how to compress the data. So because we have this advantage of all the data being in the same format, we can use database optimizers or specify to the database, if we know in advance what that data is going to look like, how to compress it so that it can be accessed quickly, but also reduce on the amount of storage that we have on the database. So having talked about some ideas of the things we're going to manage, let's dive into two examples and walk through a couple of databases that I've seen quite frequently in the wild, so to speak. The first one I'm going to talk about is Redshift. This is Amazon's MPP, and it exists in the cloud, and that's nice. Amazon's cloud is very secure. A lot of people use it. It is easy to copy from an S3 bucket and load it into Amazon. Another nice thing about Redshift is it's got a Postgres-ish flavor. It was actually based on Postgres 8.0.2. So if you're familiar with writing Postgres, it's easy to write in Redshift. It's easy to add nodes and manage the whole thing through the web console or through Amazon's API. So it is very developer friendly. And then on the pricing, it's really nice because you can add nodes, because you can spin things up fairly quickly. It's easy to scale, and you can kind of start small and grow your compute and your store. And so you can actually spin up on demand and pay hourly, or you can get a big pricing discount if you reserve an instance across a year or across 3 years. So diving into Redshift and going back to some of those ideas of what you want to leverage. When you're looking at setting up a Redshift instance and loading data into it, one of the key things you want to do for each table is think about the distribution style. And again, this is when we're thinking about loading data across different nodes, what that's going to look like. So with Redshift, you get 3 different options of how to distribute a table. And in this slide, we're looking at distributing by key. And you can see we've taken an orders table, and we're distributing the data to 3 different nodes. So on node 1, I have all the information about all the orders that user foo has made. On the second node, I have all the information that all the orders that user bar has made. And the third one has all the orders that user chew has made. And the advantage of doing this, distributing like this, is if I now join my order table to my user table, I'm going to have all of the information for each user very close to the order data. So that join is going to be very performant. So typically when we distribute by key, we're going to distribute on a join key. And again, you can see already that we've thought out about the types of queries we want to make and what joins are going to be regular, and we're going to distribute on those types of keys. The next type of distribution you can make is all. And so distribute all is actually going to write the entire table to every node in the cluster. So the advantage here is that all of your data is going to be where it needs to be for that join, and is going to lead to very fast processing times. The disadvantage here is that you've copied every row in every table to every node, so you've kind of blown up your storage. So we recommend distribution all for tables that are going to be fairly small but used frequently. Fact tables, if you have a table with a state ID going to state, that's only 50 rows. It's not going to be a big deal to distribute it across all your nodes. And then the last type of distribution style is even. And it's actually interesting that this is the default setting for Redshift. It's just going to round robin rows basically as they come in. The nice thing about this is it ensures that none of your data will be skewed onto any one node. You'll get a very even distribution, as it's called. We actually don't recommend this style usually, though, because it tends to not order the data in any meaningful way for joins or for orders. And so if you can think through the type of queries you're going to make and distribute either all for a small table or by a particularly useful join key, that tends to be our recommendation for Redshift. The other thing we want to talk about, like I mentioned, is sorting data. And so within a node, how are those rows sorted? And there's really two ways of doing that in Redshift, and I want to talk about the two. A distribution key is always going to be one key on the database because you're splitting it up by that. Since you can sort with multiple columns, you can actually give multiple sort keys. And you can do that either in a compound way or an interleavened way. So when we do a compound sort key, there's kind of a priority. In this example, first, I'm ordering by date, and second, I'm ordering by ID. So I've sorted all of my data by date, and then within a particular date, I've sorted it by ID. This is really good for, again, we're going to use this ordering when we group by in our SQL. If we order by, that's going to allow Redshift to take advantage of that sort. When we're filtering on data, Redshift's going to take advantage of that sort. And so in this case, we're saying data is most important, and then ID, and then whatever other compound sort keys we put. In the interleavened sort key, this is kind of a cool thing that Redshift has implemented. It really treats all of your sort keys equally, and the advantage of doing this is for a huge table. So this isn't going to really help you so much in your order by or your group by clauses, but if you're going to be filtering on a large table, this allows you to filter on any number of keys and it will quickly get to it. So in this case, we've got a customer ID and a page ID, and if we wanted to ask about all of the page views that a particular customer has seen, it's going to be identical to asking for all of the customers that's viewed a particular page. And so again, the recommendation for interleavened keys is going to be for larger tables that you're filtering down on a particular value, whether that be I want to see the page views for a couple of customers, or I want to see a couple of page views in all of their customers. That's going to be the better sort style for Redshift. The other managed MPP that I want to talk about is Vertica. This is Hewlett-Packard Enterprise offering. It can be deployed on premises, or just recently they've started offering it in the cloud. Just like Redshift, it's got a SQL It's SQL-based. Like Daniel said, that's a huge advantage. In this case, it's ANSI 99 SQL standard. Vertica is also an extremely feature-rich environment. So there's a lot of analytical functions with distributed R and geospatial functions. So we typically see Vertica as kind of a higher entry point into MPP databases, but is very powerful. Vertica is interesting in that it splits its logical and physical schemas. So when you create a table in Vertica, you're actually, if you issue a create table statement in SQL, that's really creating the logical store and how Vertica is going to manage that logically. But that's distinct from its physical store. So a table, in some sense, doesn't occupy any physical storage in Vertica. Instead, the physical storage is done by projections. And so this is an example of how a table is going to be projected into a database. So I can project an entire table, which is going to be called a super projection. And you can see that each projection gets its own order. So as you set up Vertica, you can think through the type of queries that you're going to put in, and you can project that table or sub-columns of that table in the appropriate order by across the database. So this is all going to one node, so you can have multiple projections on the same node. And then within each projection, you can segment the data, and different segments are going to live across different nodes. You can also do what Vertica calls a buddy projection, which is going to duplicate the projection, but it's going to store each segment on a different node. So now you have a lot of redundancy in your data, so if you do lose a node, everything will still be performant. Obviously, that's going to come at the cost of doubling the storage within Vertica. So those are some considerations that you want to make. You can set up your logical schema very, very quickly and then decide based on what queries you're going to use, how you want to make those projections and segmentations to quickly get the data back out of Vertica. I'm actually going to hand it back to Daniel now, who can walk us through a couple of examples of on-demand databases.
Thanks, Jake. So, as Jake said, we've sort of divided classes of MPPs into two groups, and obviously there are more examples of the sort of managed MPPs than we went through, but those two, Vertica and Redshift, are really the ones we see the most. And so now I'm going to talk about the other class of MPP databases on demand. And so one thing that's important to know about on-demand MPPs is they are, by definition, in the cloud. You can't have an on-demand MPP you manage because, well, then it wouldn't be an on-demand MPP. It would be one that you manage. The other thing to know about them is that, in general, the way that they make themselves on demand is by separating the compute layer and the storage layer. And I should say, I guess, what we mean by on-demand. And what we mean is that the database itself and the cloud database provider is actually doing all the management for you in terms of deciding how big a cluster to use, how to store the data, how to sort the data, how to compress the data, how to distribute the data. They're making all those decisions for you and taking that off your plate so you don't have to worry about it. All you do is you issue the query. They figure out how they're going to run that query according to your needs and how quickly you need an answer and how much you're willing to pay, and then return that query. So that's why it needs to be in the cloud, and it's also why they tend to separate compute and storage, because they're kind of deciding the data requires its storage space no matter what, but the MPP providers are the ones who decide how much compute is needed for any given task. And so I'm going to talk about two examples, and I think really there are only two examples. These are relatively new technologies. So one is Snowflake, and the other is Google's BigQuery, which has existed for a long time, but mainly as an internal Google product, and only recently has become something that's publicly available for use. So first I'm going to talk about Snowflake. So Snowflake is a new entrant, a relatively new entrant on the scene. I believe they launched in 2013, maybe 2012. And they are architected from the ground up. So unlike really all of the other examples that we've talked about, their sort of legacy and history does not go back nearly as far, which means that they had the ability to sort of define a bunch of things and make a bunch of decisions with the advantage of hindsight, and weren't sort of bound by any constraints. You know, Redshift, for example, which is Amazon's product, is actually sort of a fork of Paracel. So it's something that's existed for a long time. Redshift grabbed it, bought it, and turned it into their product. You know, BigQuery, as I said, has only recently become publicly available, but it's based on Dremel, which was Google's internal product. Snowflake is really a new thing on the scene, and so one of their big innovations is this different architecture. So rather than being a shared nothing architecture or a shared storage architecture, they are what they call a multi-cluster shared data architecture. And so what this means is you can spin up multiple virtual clusters, as they call them, as needed, big or small, and point them all at the same storage in your database. And so what they use is Snowflake runs actually inside Amazon's cloud. They use EC2 and S3, and they use S3, which is Amazon's storage layer, as a more or less infinitely expandable storage unit for the data. And so they do what they call micro-partitioning to divide your data into very small little blocks and then put it in S3 where it can be accessed by however many virtual clusters you have running at that time. And so that has real advantages because it means that you can designate different clusters for different workloads, size them appropriately, and then run them all accessing the same data set without their getting in each other's way and sort of jamming things up and seeing performance degradation. They then have sort of cloud services that manage higher level operations like security and metadata and warehouse management above that, and then those present connectors, ODBC, JDBC, or a web UI to actually run queries with. So this architecture is a new thing that Snowflake has invented and rolled out, and it's kind of a new concept in the MPP world. One of the things that Snowflake does really well, and I think this comes from their decision to sort of architect from the ground up and focus on things that people need now, one of the things that they do really well is they handle semi-structured data really well, specifically JSON data. And so you can see in this query, in the third column, you have nested JSON data. And this, for folks who deal with structured data all day, this JSON, this semi-structured data is kind of the bane of a lot of our existence because it is semi-structured. It does have structure, but that structure can change from JSON blob to JSON blob. And so, pulling pieces of data out of it is very difficult for most databases. Snowflake has a lot of really interesting and powerful tools for diving into this nested JSON, flattening it out, accessing particular values based on their key, and even organizing the JSON data in a way that makes it very performant in their database. So whereas historically you've sort of unnested and flattened your JSON before it got into your relational data store, into your MPP database, Snowflake makes it easy to load it right in as JSON and operated on it using all of the power of Snowflake. Another thing that Snowflake does that is a result of their unique architecture is they allow you to sort of scale up and scale down very easily. So, whereas managed MPP databases, generally it's quite a difficult process to scale up and scale down because you're redistributing that data and moving it around. Because their data store can be shared by multiple virtual clusters, what you're scaling up and down is just that virtual cluster. So there's no data movement required. And so that means if you have a general, sort of background small workload, you can pay a little bit for a cluster that does that. Let's say you then realize that you had a problem in your ETL, in your transformation layer, and need to reprocess 6 months of data. You don't want to wait to do that with your small cluster. You can spin up a big cluster, point it at your data, reprocess that data, and then when you're done, spin it down and stop paying for it. Snowflake is priced by the hour, and so what that means is that you can take advantage of bigger clusters as needed pay for them only as long as you use them and then spin them down. And in fact, Snowflake does a lot of work to make that automatic, to spin them down when you're not using them, so you're not paying for power that you're not using. And so that's a really neat thing about their architecture. It means that you ideally are paying less because you're only paying for what you use. And then a third thing that's pretty neat about, sorry, not a third thing that's pretty neat about Snowflake, moving on to BigQuery. So BigQuery, as I said, is Google's cloud on-demand MPP database. And BigQuery has been an internal Google product for more than a decade, but now has become one that's sort of outward-facing. And the way that BigQuery works, the reason that it can be on demand is that when you are using BigQuery, you're actually part of a huge shared cluster of nodes. And BigQuery decides on a query-by-query basis how many nodes you need to complete your workload in a relatively short amount of time. And so it will grab nodes out of a 5,000 node cluster as you need. And so if you have a little query, a select count of all query, it might only give you 50 nodes to complete that very quickly. But if you have a monster query, it might give you all of the power of that full cluster. And so this allows it to really size the compute based on the particular workload, even down to the query-by-query level, without having to do that sort of onerous scaling up and scaling down, because there is no scaling. It's on demand. Another thing that this means about BigQuery's architecture is that you actually pay per query. You are actually charged from a few cents to many dollars, depending on how many compute resources you use. So BigQuery provides a number of resources in terms of caps and monitoring to make sure that you're staying within your budget. But on BigQuery, the limiting factor is not how powerful the MPP database is. It's instead how much you're willing to pay. If you had an infinite budget, you would be able to sort of burn through any workload in no time flat. One other thing that BigQuery does that's pretty neat is it allows you to use JavaScript in user-defined functions. So this is a way that you actually can parse JSON, which is something that's often used for, because JSON is JavaScript, or it's a data form that JavaScript knows how to handle very well, and so you can create functions in JavaScript, pass them in as user-defined functions to BigQuery, and then call them within your SQL, and that allows you to do really powerful things right within the SQL context using BigQuery. And then one more thing that BigQuery does that's pretty neat is that it allows you to actually use Google Sheets, Google's spreadsheet product, in conjunction with BigQuery. And so what that means is you can actually address a Google Sheet as if it were a table in your database. And that turns out to be hugely useful, both for getting data out, in terms of writing to a Google Sheet so that you can access it in a spreadsheet, but also for getting data in. So if you have a billion row table and you need to change the mapping, maybe you have states, 50 state abbreviations, and really you want the output to have the full state names. Obviously you could do that with a big case statement inside the SQL, but a much cleaner way to do it would be to write the mapping from abbreviation to full name in a Google Sheet, join that in to your billion row table in BigQuery, and then run your query, and that works just fine. It's a really neat function that they've introduced recently. And so, it's a sort of another way that Google is leveraging their ecosystem. So the last thing that I'm just going to talk about for 1 minute, so that we don't get accused of skipping it, is that, I talked about Hadoop at the beginning, and Hadoop is a very close cousin of this idea of MPP. The big difference, I would say, is that Hadoop runs on commodity hardware, whereas MPP tends to use specialized hardware. And so that makes Hadoop relatively cost-effective. The big downside is that you don't generally get to write SQL for Hadoop. You have to write Java, although folks like Cloudera and Spark and Presto and Hive have created SQL on Hadoop implementations where you can write SQL. It can get translated into Hadoop and run against a Hadoop cluster. And so we are definitely seeing lots of folks use these, which is another way to sort of leverage massively parallel processing, even though they are not technically MPP databases. So just to wrap up, maybe I'll let Jake give the sort of quick reasons that folks choose Redshift and Vertica, and I'll give the quick reasons that folks choose Snowflake and BigQuery that we see, and then we'll do our quick wrap up.
Yeah, thanks, Daniel. So what we mostly see is Redshift is very popular, and a lot of that popularity is because it's easy entry point. So it's quite cost effective, it's fast because of all these MPP things we've talked about, and it's scalable. We see Vertica, like I said, as a pricier entry point, but it's very feature rich. It can also be deployed on premises. So for companies that need to keep the data very secure in their own firewall, that's a huge advantage. So we see, I think, tend to see bigger enterprise level companies using Vertica, but both are very performant.
Yeah, and then
Daniel?
among the on the on-demand MPPs, Snowflake, as I said, is the newest entrant, so it has that benefit of being architected from the ground up. None of that sort of legacy cruft, as you might call it, and it uses this very cool new shared disk multi-cluster architecture, and we're particularly seeing folks use it when they have semi-structured data like JSON that they need to access through their MPP database. BigQuery, is performant even with massive data sets, unthinkably huge data sets, as you might expect from something that Google uses internally. And, since you only pay for what you query, it can deliver big performance very cost effectively. So, we're going to end by just talking through, wrapping up with some very good best practices for analytics, very quick best practices for analytics, and then if we have any time, we'll take questions. So, Jake, why don't you lead off?
Yeah, perfect, Daniel. Thanks. I want to take a step back and we talk about analytics and MPP because we spent a lot of time talking about MPP databases, but what's the purpose of it? Why do analytics in an MPP? Just to get fast queries? You can call your friend over and look at how blazingly fast you can get an answer back, but that's not really what we're interested in. What we're interested in is analytics. And so it's not just reporting of metrics, but the ability to ask that next question when you see a piece of data. It's the ability to drill into that data, to alter what you're filtering on, and really understand what's happening within the data. And so the reason MPPs really can drive that is because when you get the data back, you can immediately make that change and see that next level of data very quickly. If it takes 2 minutes to get that query back, then you've forgotten the question by the time you get the data back, and you never really create that inquisitive part of analytics. And then also as you get the data, you want to share it with people so you can start getting discussion about what's underneath the data and start to drive that kind of data-driven culture that we think is really important. Now, having said that, we want to just highlight 3 things that we see as best practices when thinking about putting your data into an MPP. I love this Soren Kierkegaard quote, and the reason I stole it for this is particularly it's really useful to sort and partition your data by date. So we analyze data in time. In BI, we're always asking questions about what was this quarter compared to last quarter, what was this month compared to last month, what's happening today in my business. And if you structure your data in an MPP by date, you're going to get blazingly fast answers and be able to create that data culture. Daniel, do you want to take this one?
Sure. So the second thing is, and this really applies more to the managed MPPs and less to the on-demand ones. But when folks are saying, my MPP database is not performing as fast as I want, there are really 4 questions that you need to ask yourself. First and foremost, is your data sorted well? Sorting is a huge part of getting great performance out of MPPs, so that's the first thing you should check. The second thing you should check is your data distributed well, or is it skewed? As Jake said, there is that trade-off between having data sort of co-located on one node and having all of the nodes able to contribute equally to the workload. So if your MPP database is not performing the way you want, it's probably a good idea to check and make sure that all the nodes are able to contribute. Third thing is it compressed well? Because of that columnar schema, MPP databases can do an amazing job compressing data, often when folks are seeing bad performance, it turns out that they haven't compressed the data at all. They forgot to tell the database that it was okay to do that, and that creates real performance bottlenecks. And then, after you've examined sort of the underlying things about your tables and about the database, then it might be time to run an explain on your query and understand if your query is written in a way that takes advantage of the MPP database's abilities.
And the last kind of best practice is to think ahead. So as you're thinking about putting data into MPP, you really want to think out 2 or 3 years and plan for the type of data you see, the type of queries you're going to have, and the type of users who are going to be accessing that. So I like an Eisenhower quote here, the plan is nothing but planning is everything. So when you sit down, you want to think about what MPP is right for you based on price, based on the type of data that you're going to be analyzing and what you want to get out of that data, and who's going to be accessing it. In thinking 2-3 years out will allow you to consider switching costs and allow you to really make a best decision both on the right MPP and how you store that data and how you start querying it. And from there, I think we want to kick it to Q&A with what time we have left.
All right.
Aaron?
Thank you very much. Thank you very much, Jake and Daniel. That was outstanding, and certainly I hope our audience definitely downloaded a copy of the slides and makes note of the replay link, because that's the kind of webcast you can go back to over and over again. There's so much value. So thank you, guys. We've got a question here from Rachel. We got time for a couple. Once you choose a database and get the data in there, how do you expose it to users without losing the speed? That's a great question.
Yeah,
I'll go ahead and jump in and answer that. Go ahead, Daniel.
Yep. No, it's all you.
So we have these MPPs have SQL interfaces, and so then the question is how do you get that to people who maybe don't know SQL? Looker is a data platform that connects to databases, allows you to model the data in that MPP database in a semantic way, and then allow people to use that model to ask their own questions of the data. And so that's why we have such good expertise with these databases, is because we're used to interfacing with them to get the data out so that people can use it in a kind of point-and-click manner without having to worry about the SQL and pass that around the organization.
All right. Got a question here. This one's from Amit, and I love this question, so I'm going to ask you guys, what's the most crazy performance you've seen from one of these DBs?
Yeah, I mean, we work with more than 750 companies, and I would say the vast majority of them are using MPP databases, either one of the ones we're talking about today or a SQL and Hadoop implementation. And some of these companies are processing volumes of data that are just unthinkable, many, many terabytes a day. And these databases handle it with no problem. I know from my own experience as a customer, where we used Redshift, our tables were 20 billion rows and 40 or 50 columns wide, and Redshift had no trouble whatsoever with that.
All right. Well, again, I'd like to thank our sponsor today, Looker, because without them, we don't get a chance to provide you all with this great information, and truly outstanding information was. And more importantly, our speakers, Jake and Daniel, thank you, because you guys actually give us that information. It's really great. I certainly learned a ton, and I hope our audience did as well. Before we go, just a couple things for you and our audience to remember. First, don't forget to download a copy of today's presentation. I say it often, but it's one of those things that I think really does have a lot of value. Second, we have a very short survey. It's under a minute, and we really value your feedback because we take it very seriously that you give us an hour of your busy day, and we want to make sure we're using that in the most effective way we can and giving you the best information possible. Also, if you'd like to refer back to this event, as I mentioned, there'll be a recorded version. That'll be available in about 24 hours, and that will be at www.eseminarslive.com. Just type in the search bar Looker, and you will get to this event. And while you're there, you can check out our calendar of upcoming events. With that, this is Aaron Goldberg. I'm your moderator today, and I want to thank you for your time. We really appreciate that you make us part of your busy day. And again, my sincere thanks to Looker and our speakers, Jake and Daniel. With that, have a great day and have a great week.